Hello, welcome to chapter 4, I guess. I titled this chapter 4.0, but actually this subtopic really have no place to be in the syllabus because it is kind of like across the board from kinematics to dynamics because we are going to talk about air resistance or drag force. So previously in chapter 3, right, whenever you do kinematics considerations, most of the questions we omit air resistance simply because air resistance is a very finicky thing. If it's just a constant number that we can subtract from the value of G or 9.81 or whatever force there is, then that would not be a problem. But sometimes air resistance is a bit complicated. So let us start by trying to understand what drag force or air resistance actually is. Okay, so when a solid object moves through when a solid object moves through a fluid, such as air and water, it will collide with the particles of the fluid. So for example, when you are, let's say, walking around, moving your hands around, you will feel the air particles colliding in your skin, which is kind of like a long-winded way to say that there's wind, there's air movement. Okay, so it collides. So it will collide with the particle of the fluid. It's a little bit like you swimming. So let's say you are swimming in the water, you are pushing the water particles away. The water is actually giving you drag force. Okay, so all of this is what we call resistance to motion. So if they ask you to define drag force, okay, we can call it the resistance to the motion of a solid object when it moves through a fluid. Okay, so drag force is the resistance to motion of a solid object as it moves through the fluid. So this fluid can be air. Air is a fluid because air can fluid. Okay, or it could be you walking inside a swimming pool or trying to swim. All this will have some form of drag force. If the object is moving in air, we will call it air resistance. Okay, so drag actually depends on the properties of the fluid. Like for example, is the fluid viscous or if the fluid not viscous? So for example, the drag force in a fluid like oil will definitely be a lot more than the drag force in a fluid like air or water. Okay, so it also depends on the size, shape, and speed of the object. Okay, now this equation is not in your syllabus, but sometimes you will encounter this because they will give it to you to remind you to consider drag force, FD, in this kind of expression. So the important takeaway here, right, is that this drag force or air resistance depends on how fast the object is moving. Because the faster you move, the quicker the particles will collide against you, the more resistance you will experience. That's why your drag force, or like for example this FD, will be proportional to V square. You can see this V, right? Where V is the speed of the object relative to the fluid. So the faster the object is moving, the faster you are running on the field, you will feel that the air is pushing you back faster and faster. Or let's say your car is driving very fast on the highway and you open the window and you stick your hand out, wow, you feel the air, feel the drag, dragging you back. Okay, of course, this is also dependent on the density of the fluid as mentioned. So whether the fluid is viscous or not viscous. It also depends on the drag coefficient and the cross-sectional area. So a little bit more about drag coefficient, right? You can see it depends on the flow. All right. So if let's say you are looking at this kind of shape of flow, very thin, very aerodynamic, then these two will have very little drag force. The ball has some drag force but still okay. This drag force of this shape, because it's like running around with a big manila cardboard, so they will feel the air resistance in its entirety because it's a flat, large surface area. So the surface area matters and also the shape of the object matters. Alright, but the important thing that you need to know is actually this one. Drag force is proportional to V square. The faster an object moves, the larger the drag force will be. And why is this important, you may ask? Well, remember this thing that we learned called free fall? So let's say an object is in free fall. Maybe, for example, a ball. You drop a ball from a very, 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 very tall building. Okay? So when you release the ball, right, at this point, T is equal to 0, U is equal to 0, the ball begins to drop. And when this ball drops, what happens is that it will pick up speed. So maybe when it first falls, right, at this point, the speed is very small. So at this point, your V is small and your drag, okay, I'm just going to use the symbol, FD is also small. Okay, but as you travel faster and faster, suddenly FD will become larger and larger. So this is the speed law, V1, let's say this is V2, let's say this is V3. So this means as you travel faster and faster, your FD, as I travel in this direction, your drag force will begin to increase. Okay, so let's consider the fact that if the drag force is increasing, then I'm now going to draw a diagram to represent the forces acting on the object. So let's say we draw at the starting position. This is what we call a free body diagram, or the diagram of forces on the object. You will have mg. In fact, your object will always have mg. So I'm just going to copy the mg. This mg is so constant that at every single point is going to be the same. Because why? Gravity is a constant friend for now until A2. Alright, so I'm going to represent the drag force. At this point here, your drag is 0. So there's no vector for drag. D is 0, or Fd is 0. Then here your Fd is really small because the velocity is small, and gradually your Fd become bigger and bigger until this point, let's say at this position, at this particular height, V3, your Fd and mg is equal. So this is what you know as balance forces, or resultant force is 0. Now if the resultant force is 0, this means that the object is not accelerating, or it's not moving faster and faster. It is maintaining the same speed, which means at this point onwards, let's say here is V4, V3 will be equal to V4. And this is what we call terminal velocity. Terminal velocity because your speed is the same already, it won't change anymore, stay the same. Terminal, like a flat terminal. So I'm going to draw out that velocity time graph for you later. But it also, so here this because there is no unbalanced force, or your net force is 0. So because of this, from the equation, F is equal to ma, although I haven't introduced yet in this syllabus at this point in time, but if you know this, you should lah. If not, why are you doing physics? You are, right? You're in the right channel, right? Okay, so as what we all know, F is equal to ma, so A will be equal to 0 because your net force, this F is net force, is equal to ma. Alright, so if you are confused about how to use the equation, you just wait for the further lectures from chapter 4 lah. But basically, whenever there is no resultant force, you're not pulling the object, the velocity of the object will not change, the velocity will stay the same, and that is called terminal velocity. So if I plot a graph of, let's say, V against T, so you have done enough past year questions from chapter 3, you will know that the graph looks like this. And then eventually it will flatten out. Okay, so you can see from here to here that the gradient is decreasing, meaning acceleration is decreasing. And the reason why acceleration is decreasing is because as you travel down, Fd increases. If Fd is getting bigger and bigger, the green arrow is getting bigger and bigger, it means that the net force will decrease because it is fighting against gravity. So the net force will decrease. So it will decrease until drag force is equal to mg, the weight. Alright, so this one you already know already, acceleration decrease, and then at this point onwards, you will get a flat line, or I will try to draw a flat line. Okay, so here is what we call, here to here onwards, this is what is known as terminal velocity, meaning this V here, based on my drawing, this will be V3. Okay, so it will stay that same speed all the way. It won't travel faster and faster anymore. Why? Because your velocity is constant, your drag force henceforth will become constant. So from here onwards, V constant, A is 0, net force is 0. This means your drag force is also constant. Alright, so hopefully that is clear. And the next part, we will go through 2 examples. I'm going to start off by doing a question. So this one, drag force, is given by this equation. Do it yourself lah. Show that C has no units. I think this one I can leave it to you. Let me know if you need help, okay? So a raindrop falls vertically from rest. Drag force is the air resistance because you travel very fast. But initially, we assume the air resistance is negligible. So sketch a graph to show how time and velocity of the first 10 seconds of the motion changes. So if you remember this equation, V equals to U plus AT, the raindrop is free falling if there's no air resistance. So I'm just going to put 0, 9.81 and 1 here. So you can see that after 1 second, the speed would have increased from 0 to 9.8 or 0 to 10. So in 1 second, I'll go from 0 to 10. Okay? I'll draw around like slightly under 10. Okay, so then you are asked to calculate the velocity of the raindrop after falling 1000 meter. Sure. So your S is 1000, T you don't have, U is 0, V you want to find, and A is positive 9.81. Treating downward as positive, okay, so that your S can keep as positive. So since we do not have, see the arrow there, downward is positive. No T, we'll use V square is U square plus 2AS. Okay, so sub the values in, and you will get a very large speed, my friend. 140 meters per second. So fast. Okay, but of course cannot reach this fast lah, because in practice the air resistance is not negligible. So because there's drag force or air resistance, and drag force is state an equation relating drag force acting on the raindrop when it's falling at terminal velocity. You know airplane terminal. So terminal velocity is when the velocity doesn't change. So some of you actually ask me what I intend to draw in my notes when I say a parachutist jumping off this graph lah. I intend to draw this graph. I'll draw it here for you. Okay, so this one, parachutist falling from an aircraft, is shown. Okay, I'll go through part by part in the graph, and this will probably take a while. Feel free to pause anytime. So you can see at point A, the beginning part of the graph, it's a straight line. Straight line because the raindrop or the parachutist is just falling down. So the predominant force here is mass, because the value of the drag force or air resistance is very small. Just only fall the speed is very slow. Okay, and the acceleration is about constant, so you kind of get a straight line in the beginning. And then when the gradient begin to become less constant or begin to flatten out, this is when your velocity is large enough so that now your drag force D is significant. So if I'm going to draw mg like this, okay, so let's compare. You can see this D is quite small. Okay, then D becomes bigger and bigger because the the parachutist is falling faster and faster. Now, D will increase until it's equal to mg. Now, once it's equal to mg, there is no way that it can travel faster anymore. Equilibrium, mg equal to D. So BC is what we call terminal velocity. When mg is equal to D, the net force is 0. So your acceleration is 0. Okay? So when you're transitioning, right, from A to B to C, when the gradient begins to decrease, it's because the net force decrease, acceleration decrease. Now at point C, sudden changes happen. This is because the parachute opened, the drag force increased a lot. So you can see D suddenly just blew up, increases rapidly. So because of this, your net force went from 0 to upwards, very large upward net force. So the parachute will slow down very quickly. Okay, slow down rapidly at where I draw the blue line. All right, and then finally, right, at point D, okay, the drag force will decrease because you slow down already, ma. So your drag force has begun to slow down, decrease again. So at DE, it's slowing down, so your D will decrease back. And because your D decreases again, your drag force decreases again, the acceleration will decreases in magnitude, so the gradient is getting less steep. It's the same idea. Okay, just like in the beginning, when you open the parachute, the acceleration increased, but the magnitude also increase in opposite direction. Now finally, you notice after E, it flattens out because, yay, D equal to mg again. So your drag force decreases back such that it is equal to mg. And once again, you will get your terminal velocity. Okay, so at positions of terminal velocity, I will highlight here. And the idea of terminal velocity is because your acceleration has decreased to 0. Now this is a family favorite. Favorite to us in objective, sometimes they ask in structure. But the concept of it is very important. So if you're confused with this, arrange to come and see me, okay? So in the beginning, you can see drag force very small, increase, increase, increase until the speed can no more increase because it balances off the mg. You have a high terminal velocity. I kind of don't want to die. So we'll maintain at BC first. And then after that, it will drop. Okay, it's going to drop very fast because when you open the parachute, drag force becomes very big. So your speed will begin to decrease again. So your speed will decrease until your drag force decreases together and you reach terminal velocity. So we're going to define some stuff, or just to fill in the question. We define acceleration as rate of change of velocity, and Newton's first law will be an object will not change its state of motion unless acted on by an external force, aka the law of stubbornness. You won't change until you got external force. Okay, so let's see. Calculate the distance traveled by the parachutist in the first 3 seconds of the motion. So in the first 3 seconds, right, we know distance is area under the graph, so we're going to just super zoom in. So only nice thing nice about having a digital paper is you can zoom in. 3 seconds. So this scale is a little bit odd, but not very odd. It's just they label every 2.5 boxes. So 3 cm, so in the middle between, so I think this is 6. It's like 1 cm is 2. So you'll notice that all the graphing is a bit cha-cha. Okay, so 3 cm is somewhere here. I'm just going to extrapolate here so that I can get a value. Because this looks like a triangle to me, thankfully. If not, we have to count boxes. I'll do an example where you need to count boxes later. Okay, so we're dragging it upwards. And I think at 3 seconds, I will nicely hit 30. Okay. So yeah. So it will be half times 30 times 3. Area under the graph. And that, my friends, will give me 45 meters. All right. Okay. Explain the variation of resultant force. Only talk about the force, don't talk about other stuff, unless you're explaining why the force is like that. So at t equal to 0, which is point A, the resultant force is very close or equal to mg, and it's constant. The weight of the parachutist. Okay, this is because, don't forget, you have to explain the drag force is small or negligible due to the slow speed or the small velocity of the parachutist. Okay, then when your speed is large enough, so as v increases, because don't forget the thing is free falling, you will encounter more and more drag force. So drag force increases, your resultant force decreases. Okay, because they're in opposite direction, it decreases until point B, because point B is where it flattens out, where it is equal to the magnitude of the weight. So when drag force is equal to the magnitude of weight, resultant force from B to Z is 0. So my sentence could be made better if I change the if I just add a point at point B, drag force is equal to the magnitude of the weight. All right. So resultant force from B to Z is 0, as both speed and drag force remains constant. So I'm going to show you roughly where the marks are. If you say the resultant force is constant and equal to the weight because drag force is negligible, there is 1 mark. If you say drag force then increases because the speed increases, and because of this resultant force decreases, that's the 2nd mark. And then you say at point B, drag force is equal to the magnitude of weight and resultant force is 0. This is the 2nd mark. So the resultant force is 0. Speed don't change, drag force no change. Okay? Same thing happens after you open the parachute. Drag force too big, you slow down, drag force decrease until equal mg. Same speed. You can land safely. Anyway, describe the changes with the frictional force on the parachutist at 15 seconds. So increases suddenly at a large magnitude because you open the parachute now. Okay? So between 15 seconds, the friction will decrease because you already slowed down. Anyway, mass of the parachutist is 95 kg. Calculate the average acceleration and the average frictional force between 15 to 17 seconds. Now, my friends, 15 to 17 seconds, again, good thing it's a straight line. It looks like a straight line. I shall assume it's a straight line. If you have actual physical paper, you can put your ruler there and check whether it's a straight line or not. But online, so you can use a ruler or a tool. If you're wondering what I'm doing, I'm trying to find 15 and 17C. Okay? And I'm trying to read the graph. So the whole idea of having a parachute is to suddenly increase your drag force to slow you down, such that when drag force decreases and d equal to mg again, it will be at a lower speed. And then you can be safer, and you can just do it again. All right, anyway, 17 is somewhere at 20, I think. And 15, now you can see the pens I use. I tend to show the extrapolation because some syllabus requires you to show it, but A-levels, they're not that strict about us checking whether you indeed read from the graph. But you can also make it a habit. Anyway, it looks like 15 seconds, it will be almost precisely at point C. And that is actually, I think, 50 meter per second. Alright. So you kind of like decelerated from 50 to 20 in 2 seconds. No bad. So you can use A is gradient, or V minus U over T. So 50 to 30 divided by 2. Negative I put outside because decreasing, so the gradient is negative. Okay, so 50 minus 20 divided by 2. Think. I'll get negative 15 meter per second square. Okay, to find average frictional force, I'll use F is equal to ma. Let's consider the forces. We have drag pointing up, we have mg pointing down, and the acceleration is negative upwards. Upwards is negative in this question. Okay, slowing down. Upward is negative, downward is positive. Alright, anyway, you just take mg minus d is equal to ma. So you can just find d here, negative 15. If we're treating up as negative, because the parachute already open, so your acceleration has to be upwards. Then you slow down as you fall downwards. Okay. Later I'll show you what happens if you flip the sign convention. Okay, so you'll get 1860, I think. Oh, yeah, I made a mistake. I thought the parachutist is 75 kg because I'm thinking of Asian weights, you see. But actually, it's Angmo weights, 95. Okay, so correct already lah, this one. Anywho, if let's say you use F equal to MA, but you flip the signs, meaning you take up as positive, down as negative, okay lor. So you have D minus mg is MA, D which will be MA plus mg, which is 95, my bad. I don't know why I keep thinking he's 75. And then the A and G, 15 plus 9.81 because we're treating upward as positive. You get the same answer, okay? Alright, so based on this understanding, we can write the equation for the forces acting on the raindrop when it's falling at terminal velocity lah. We will have the so-called friction or drag force. Now I'm checking here to see what, okay, they also use D for drag force. Use the symbols that they give, you don't invent your own symbol. It is different for every question. So you have D and you have pulling upwards and mg pulling downwards. So at terminal velocity, D equal to mg, where m is equal to mass of the raindrop. I tend to define any symbols that is not mentioned in this question, just in case. Okay, you have the mass of the raindrop, cross-sectional area, density of air, and the initial velocity of the raindrop is 0, value of c is 0.6, so the terminal velocity is 7. So I'll give you so much numbers, confirm it's a substitution question now. So you get D is equal to mg, and you can substitute the whole chunk on top, c rho a v square is equal to mg, because at terminal velocity D equal to mg. So you rearrange, you get this equation, then you substitute, making sure everybody is SI. You know, whenever you substitute into a physics equation, especially if it involves a physical constant like 9.81, it's like doing a photo shoot for the family. You have to make sure everyone wear nicely. You have to make sure all your units convert to SI. Okay? If you're not sure, just convert. Better to dress up than to dress down. Better to convert and not need to convert than forget to convert but need to convert. Alright. So 7.33 meter per second. So it's about 7. So the raindrop reaches terminal velocity after falling about 10 meters. Now draw, sketch the variation of Vt. So you expect the plateau to happen at 7, not 10. You cannot reach 10. Drag force doesn't allow you to reach 10. Too bad. Raindrop. So I'm going to take 7, okay? I assume I cannot plot 7.33 how to plot. So 7 is here, okay? Then I got a slight problem. I know that it will be a curve following the shape of the graph that I showed you just now. I just don't really know where the 10 meter will be. So if you check the area under this graph, right? The graph that of the straight line, the triangle, this area is 1 times 10 divided by 2 is about 5. So whatever area under the graph before I hit terminal velocity, it should be double the area of the triangle. Ish. Double-ish. So you don't go and, this one is definitely too soon. So no. Need to go stun. Later. Maybe need to be severely later. Okay, so you need to travel 10 meters, double this area. So because this area is only 5. Area of the triangle is 5. So you kind of like need to, okay, again, I'm going to keep redrawing it until it looks correct to me. Okay, so again, the area under the curved portion should look about double the area of the triangle. I'm just estimating. Anyway, it's 2 marks. So 1 mark is when your terminal velocity is 7. And because the time is very big, so the time for you to hit Vt is between 1.5 to 3.5. Pretty large. Anyway, you cannot really tell the time when it hits terminal velocity because you don't have enough information. Alright? Okay, so go try some questions and good luck. Make sure that your physics is not free falling. Please open your parachutes so that your results will not fall too low. It will go up. See you in the next video then. Bye bye.